Introduction to Functions and Relations. So we'll give a precise definition of a function in a few minutes, but first let's just consider this example. Construct a table and graph for the function y equals 8.5 times x for the values of x between 0 and 40. So over here you can see that we plug in certain numbers for x. Here I have 0, 10, 20, 30, 40. And when you plug them in, you get the corresponding values of y. And that creates the following ordered pairs. And then when you graph it, you just need to make sure that your x-axis and your y-axis are scaled appropriately. So for example, on the x-axis, we need to have at least the values from 0 to 40. And on the y-axis, we need to have the values at least from 0 to 340. And you can see what they did here is they scaled it by increments of 50 units. So this equation here is what we would call a function. And the primary reason for this is because when you plug in an x value, say for example x equals 10, you get precisely one output value. So that is, it is well defined. When you plug in 10 for x, we get 85 for y. So in general, when you have a function, you will have a domain. This is going to be the set of all the input values. And then the function is going to take those input values, and according to some kind of a mathematical rule, it will produce another value, which belongs to the set that we call the range, and this is the set of all the output values. So for example, in the previous problem, if we wish to state the domain and range for the function y equals 8.5 times x, where x is a value between 0 and 40, notice that this is the domain, right? They imposed this domain on the function. So the domain is the set of all x such that x is a value between 0 and 40. Now, when you plug in these values, what are the y values that you get? So if you remember from the table on the previous slide, the range is going to be all the y values starting at 0 and going up to a maximum value of 340. Now again, in this case, this domain was imposed on the function and the range is a consequence of that. Just for clarity, if they did not impose this here, the domain of this function would be all real numbers, right? Because there is nothing that we can't plug in for x. It's just that we're choosing to plug in values between 0 and 40. Now let's define a function. A function is a rule that pairs each element in one set, called the domain, with exactly one element from a second set called the range. Another way to think of this is a function is a set of ordered pairs in which no two different ordered pairs have the same first coordinate. The set of all first coordinates is called the domain, and the set of all second coordinates is called the range. So what does that mean when they say no two different ordered pairs have the same first coordinate? Well, let's assume that they did have the same first coordinate. So as an example, suppose you were given a graph and it looked something like this. And let's suppose that this is x equals 5 right here. And when you plug in 5, you get a value on the y-axis. Let's say that that value is 4. And then down here you get another value on the y-axis. Let's say that that's negative 4. So notice that when I plug in the number 5, I am getting two different y values. This cannot happen in a function. So notice that if this does happen, then one point on this graph would be 5, 4. The other point on the graph would be 5, negative 4. So notice that we have two different ordered pairs, but they have the same first coordinate, okay? So if you have a function, this is not allowed. Next, let's consider the following modeling problem. Softball toss. Kendra tosses a softball into the air with an underhand motion. The distance of the ball above her hand is given by the function in symbolic form as h equals 32 times t minus 16 times t squared and this is only valid for values of t between 0 and 2. H is the height of the ball in feet, and t is the time in seconds. Construct a table that gives the height of the ball at quarter-second intervals, starting with t equals 0 and ending with t equals 2. Okay, so we have the table here. So we're going to start with t equals 0, and then 1/4, 1/2, 3/4, 1, and then 5/4, which is 1 and 1/4, 3/2, which is 1 and 1/2, and 7/4, which is 1 and 3/4, and then finally 2. If you plug these values of t into the function, you can see that we get the corresponding values of h. So what this means, for example, if I just pick one of these, when t is equal to 5/4, which is the same as 1.25 seconds, this gives us an h value of 15 feet, okay? So what that means is that after 1.25 seconds has passed, the ball will be 15 feet in the air. Now, if you graph all these points, you can see we have the time down here on the horizontal axis, and we have the distance or the height of the ball on the vertical axis. And what you can see is that the ball goes up, reaches a maximum height of 16, and then comes back down. And this is a graph of a function, because notice that when you plug in a particular value of t, you only get one value for h. Now let's consider the following example. Table 3 shows the prices of used Ford Mustangs that were listed in the local newspaper. The diagram in Figure 4 is called a scatter diagram. It gives a visual representation of the data in Table 3. Okay, so here we have some Mustangs with the year that it was made and then the price. So notice that in we have a 2010 model that has a price of $18,999, and then we have another 2010 model that has a different price, and yet another 2010 model with a different price here. And you can see that this continues on down through the table. Now, when you graph these over here, notice that in that year 2010, we have 3 different values in terms of the price. So this graph right here is not a function, right? That cannot happen. For the same model year, we have 3 different prices. So if this were a function, then every model 2010 Mustang would sell for the same price, right? Of course, this is not realistic, because when you go to buy a car, there are many things that determine the price of the car. So in the real world, there are examples of things that are not functions. So in that last example there, what we were talking about is a relation. So a relation is a rule that pairs each element in one set, called the domain, with one or more elements from a second set, called the range. Notice that the difference between this definition and the function definition is that it is paired with one or more elements from the range. Whereas if it's a function, this was exactly one element from the range. An alternate definition, a relation is a set of ordered pairs. Okay, period. There's no stipulation on what those ordered pairs need to be. The set of all first coordinates is called the domain, and the set of all second coordinates is called the range. So let's sketch a graph of x is equal to y squared. So you'll see we have a table over here. Now, the way I'm going to sketch this graph is I'm going to choose values for y and then get corresponding values for x. So if I choose y equals 0, we get x equals 0. If I choose y equals 1, x is going to be 1 squared. If I choose y equals negative 1, x is going to be negative 1 squared, which is still 1. Okay, and so on and so forth. And if I graph all these ordered pairs, you'll notice that we get a graph very similar to the one that I mentioned a little bit earlier. Notice that this graph is a relation. Check, it is that, but it is not a function. Okay, and the reason it's not a function is, once again, we have some points, for example, these 2 points, where we have the same x coordinate, but different y coordinates. And that can't happen if you have a function. Another way to think of this is that if you draw a vertical line, and if that vertical line hits the graph more than once, that means it is not a function. And that is something that we call the vertical line test. And so the vertical line test simply states, if a vertical line crosses the graph of a relation in more than one place, the relation cannot be a function. Or we can say, if no vertical line can be found that crosses a graph in more than one place, then the graph is a function. So look at these two graphs. Imagine if you were to draw any vertical line on this graph, you can see that every vertical line that you can possibly draw is only going to hit the graph one time. So this graph is a function. However, as I just mentioned on the previous page, if you draw a vertical line here, you clearly hit the graph more than once. And so this is not a function. So the vertical line test gives you a very simple way to determine whether something is a function or not, but you have to have the graph to do this. Let's graph the equation y equals 1 divided by x. So this can be a little bit tricky, but if I plug in a value like -3, y is going to be 1 divided by -3, which is -1/3. If I plug in -2, we're going to get -1/2, etc. Notice that if you plug in 0, it's undefined because 1 divided by 0 is undefined. Now to graph this, I need to plot these ordered pairs. So first we have the ordered pair -3, -1/3. So -3 is right here on the x-axis, and -1/3 is right about here on the y-axis. So that point is going to be right there. Next, we have -2, -1/2, which is going to be right about here. Then we have -1, -1. -1/2, -2. So x equals -1/2 is right about here. Y equals -2. And then finally, -1/3, -3 is right about here. And if I go to sketch this, notice that the behavior goes like this, because we cannot plug in the number x equals 0, right? We tried, but when you plug in 0, you get undefined. So what we have here on the y-axis is called an asymptote. This graph here cannot touch the y-axis. So if I were to extend the y-axis downward here, this graph is just going to get closer and closer to it, but it's never going to touch it. Also, over here on the left side of the graph, this is going to continue to rise, but it's never going to touch the x-axis up here. Okay, so this is going to keep on going, but it's never going to touch. Now, if we graph all of these other points here, right? So 1/3, 3, that's going to be right about here. 1/2, 2, 1, 1, 2, 1/2, and 3, 1/3. And you notice that you get a very similar looking picture over here. And so this graph is very different from lines and parabolas, etc. We'll talk more about these kinds of graphs in the future. Next, let's talk about the graphs of y equals the square root of x and y equals the cube root of x. If you look at the graphs on the positive side, okay, so if you look at it over here and over here, you should notice that the graphs are kind of similar to each other. The main difference is there is no left-hand side of the graph for the square root of x, whereas there is a left-hand side of the graph for the cube root of x. Now, why is that? Well, remember, when you try to plug a negative number into a square root, it's undefined. It's actually a complex number, but in terms of graphing, we can't graph that here, so we say it's undefined. So the domain here is you can only plug in values of x from 0 to infinity, right? Or I can say x must be greater than or equal to 0. And then the corresponding range here is also 0 to infinity, meaning that y is also always greater than or equal to 0. And you can see that because the graph here covers the positive side of the y-axis, but it does not cover anything down here on the negative side of the y-axis. Now, the cube root of x is a very similar graph, except that now we can plug negative numbers in. For example, the cube root of negative 27 is negative 3, right? So we can plug negative numbers in, and this completely changes the domain and range. Here, the domain is all real numbers, right? Because we can plug in any value from negative infinity all the way to positive infinity. And the range is also all real numbers. So in other words, the x values and the y values can be anything in this graph. Next example, the manager at Albert's Appliances has $3,000 to spend on advertising. A 30-second spot on a television costs $150 per broadcast, and a 30-second spot on radio costs $50. The manager decides to buy X television ads and Y radio ads. Write an equation relating X and Y. Okay, so first we're going to say X is the number of TV ads and Y is the number of radio ads, which they told us to do up here. Now we got to figure out, how is this all related? Well, remember, a TV ad costs $150. So if we have X TV ads, the total cost for the TV ads is going to be 150 multiplied by X. And for the radio ads, if we have Y of them, the total cost here is going to be $50 times Y, because the radio ads only cost $50. And then the grand total, in terms of the money spent on advertisement here, is going to be 150 times X plus 50 times Y. And we know this has to equal 3,000 because they have budgeted $3,000 for their ads. Okay, so next we want to make a table of values showing several choices for X and Y. So one choice, of course, is we could let X equal 0, right? If I let X equal 0, that means we have no TV ads. And if X is equal to 0 in the equation, we get 150 times 0 plus 50 times Y is equal to 3,000. This cancels out, and if we divide by 50, we get Y is equal to 60. So if we do 0 TV ads, we can do 60 radio ads. On the other extreme, if we let Y equal 0, so in other words, 0 radio ads, then the equation becomes 150 times X plus 50 times 0 equals 3,000. 50 times 0 is 0, and if we divide by 150, we get X is equal to 20. So if we do 0 radio ads, we can do 20 TV ads. Now, of course, you can do any combination of ads as well, but we know no matter what, we can never have more than 60 radio ads, and we can never have more than 20 television ads. So let's suppose that we let X equal 10. So let's suppose we do 10 TV ads. Then the equation would become 150 times 10 plus 50 times Y is equal to 3,000. 150 times 10 is 1,500. To solve for Y, I'm going to subtract 1,500 from both sides. And that is going to give us 50 times Y is equal to 1,500. And dividing by 50, we get 30. And so if I put these values into a table, and again, you can find more values if you want, but when X equals 0, Y was 60. When Y equals 0, X was 20. And when X was equal to 10, Y was 30. Okay, so there's a table, and now I'm just going to plot these points and graph the equation. So here's my graph. I just need to scale it. So notice that the x values go from 0 to 20. So let's say this is 10 here and 20 here. And then the y-axis goes from 0 to 60. So let's say 20, 40, and 60. Now, if I plot these points, we have the point 0, 60, 20, 0, and 10, 30. And you can see that this makes a straight line. And that's all of the graph. Okay, the graph does not continue in this direction. It does not continue in this direction because in this problem, it doesn't make sense to have a negative number of any of the types of adds. Okay. Now, any point that is on this line would be a possibility in terms of the number of ads that you could do for both the television and the radio ads. So the nice thing about having a graph is you can see the more television ads that you decide to do, the fewer radio ads. And likewise, the more radio ads you decide to do, the fewer television ads. So it just gives you a nice picture of what's happening here. And that concludes this video lesson.